Okay, let's do a quick summary of last time. And even if you think you remember the stuff from last time, please rewatch the summary. You can watch it at double speed if you want. I just want to make sure that everybody's starting from the same place in your minds. So hash maps provide constant time storage and retrieval. So what that means is two things. You've got a put method, which will let you store key value pairs. So remember, you're looking up one piece of information using another. So in this case, we've got names and favorite kinds of pie. So I'm storing Mr. D, which is the key, and blueberry, which is the value associated with the key. Then later on, I can retrieve the information using the get method. So if I say get Mr. D, it will retrieve the value that's associated with the key Mr. D. It will retrieve blueberry as my favorite pie. So what it means that this runs in constant time is that the amount of time it takes to run both operations is independent of the total number of things that I've stored inside my map. So it'll run in the same amount of time if I've got 10 things or 10 million things. And this is counterintuitive because if you imagine that you're just saving these into a list, if I want to retrieve Mr. D's favorite kind of pie, it seems like you have to search through everything in the list. And it seems hard to imagine how you're going to find Mr. D without searching through everything in the list. But that would be big O of n. It would take longer the more things that there are in the list. So that's the kind of big question, is how do hash maps achieve this constant time storage and retrieval? And here's how. A hash map uses an array as its internal storage, and we're going to imagine that the array stores objects that contain both the key and the value. So when I run put on Mr. D and blueberry, we take the key and you run the key through what's called a hash function. And the hash function is going to take that key and turn it into an integer in a particular range. How it works depends on the hash function. But that's not important for us right now. Let's just imagine that Mr. D ends up mapping to the integer 5. So 5 is now the unique location where we're going to save the key Mr. D and the value blueberry. So the hash function is going to give you the indices where you store your information. You want to be able to actually visualize kind of in detail how this works. So on the right here is an implementation of what I've described so far, and there's like a really critical detail, actually a couple, that this doesn't cover. But I'm imagining I have an entry class that has two strings, a key and a value, and I'm making an array that by default is 100 entries long. And for put, what I'll do is I'll start by creating a new entry object for the key and value I want to store. Then I'll calculate the hash of my key, and that gives me an index. And then I'll go ahead and store my object directly there. For get, I would only have the key as an input. I would use my hash function to calculate the index where I would have stored it if my array contained that key. And then I go ahead and get the object which is located at that index. Well, if it turns out I'm searching for something that's not there, then the hash function is going to give me an index where nothing is stored because I never actually stored anything with that key. And in that case, entry will be null. So first I check to see if it's null. And if it is, that means I'll return null from my get method because I want to indicate that that key doesn't exist. Otherwise, that means I did store something there, so I can ask my entry object what the value was. Okay, so what are the critical details that we're missing here? Well, the most obvious one is what happens when there are collisions? What happens when two different keys are mapped to the same index by your hash function? And there's actually a whole bunch of different ways to handle collisions, and we'll talk about those in a second. The other is the idea of a load factor. So as your array gets more and more full, collisions are going to become more and more frequent. And at a certain point, you're going to want to expand the storage capacity of your hash map. So you're going to want to create a larger internal array. So kind of how do you think about the issues surrounding that? So I said last time that there's lots of strategies for handling collisions, and here are several. And I described chaining to you, which I'll summarize briefly now. So the idea of chaining is instead of having each element in your array be able to store one object, you want each element in your array to be able to store a list of objects. The traditional way of implementing this is using something called a linked list, but we haven't talked about that. So you can imagine it as if we had created an array of array lists. So each array element contains an array list, and then if two keys hash to the same index, you can just chain the objects off of each other in the array list at that element. Two things to note are that it actually takes a lot of time and memory to create all of those lists. And the other is that this introduces a worst case big O of n behavior. This worst case behavior would only happen if everything that I put into the array that I put into the hash map hashed to the same index. So instead of distributing my objects throughout my array, I would really just be adding all of my objects to the array list at a particular index. So the worst case behavior would be unusual, but you can see that you could approach the worst case behavior if you had a hash function that wasn't very good and didn't distribute your keys uniformly, if your hash function ended up creating a lot of collisions. Okay, let's review what we said about the load factor. So typically you'd have a maximum load factor, which is a percentage. So you'd say something like, my array should never contain more than 65% data, or it should never be more than 65% full. So then you check whenever you put a new thing into your hash map, have you exceeded your load factor? Is it now storing more things than you want? And when it does, then you grow the size of your storage the same way that we did for array list. So I'm suggesting that we're going to create a new array that's twice as long. But you need to rehash everything. So you need to reinsert everything into this new array rather than just copy all the values over the way that we did for array list. So why can't you just copy the values? What's the problem with that? The problem is that you're going to end up failing to look up things that you've already stored, because for a longer array, your hash function is going to generate a different location than the one that you originally stored it in. So let's look at a quick example. Let's pretend that my array is length 100. I put Mr. D Blueberry, so I run Mr. D through my hash function, mod 100, because that's the length of my array, and I get 84. So I store Mr. D and Blueberry in index 84. Okay, let's pretend that now I've exceeded my load and I create a new array, a length 200 array. And let's pretend I was just going to copy all the values straight over. So the index, oh, my index has changed. Hold on. Okay, fixed. So in the new length 200 array, my object is still at index 84. Okay, let's say I try and retrieve it now. I say get Mr. D. I'll run Mr. D through the hash function, but now the hash function is modding by 200 because that's the new length of my array. And because I'm modding by a different number, it's going to end up finding a different index. So it's going to look inside index 148 instead of 84, and it's not going to find anything there. So I'm going to break my ability to look up the values that I've already saved. So what's the solution here? The solution is not to try and remember like what was the mod that you used when you originally stored it. That's gonna be a nightmare to keep track of. Instead, you just want to reinsert everything by using the hash function with the new array size. And if you reinsert everything with the new array size, now when you look it up, you're sure it's going to work.